Okay, so today we start with a new chapter, which is on differential amplifiers, and this is how our discussion is going to proceed. We'll look at differential amplifiers initially from the point of view of building amplifiers on an IC. And if you want to build amplifiers on an IC, then you cannot use large coupling capacitors, large coupling and bypass capacitors. And we'll see that differential amplifier is a natural solution to a biasing problem where capacitors are not available to help with coupling in and coupling out of signals here. And we'll then see that differential amplifier have interesting properties of rejecting common mode signals. And after covering these two, then we'll go ahead and do our usual DC analysis and small signal analysis of differential pairs here. All right. So the first two parts deal with the motivation behind differential amplifiers here. All right. So let me set up the problem here. We have seen this particular circuit of a common emitter amplifier with a resistive biasing here. And we have seen that in this particular circuit, what you require is a capacitor from this end to couple in the signal. You require a bypass capacitor here, and you require a capacitor to couple the output signal to the load here. And these capacitors are typically, if you want cutoff frequencies, lower cutoff frequency in the range of, let's say, a kilohertz or hundreds of hertz, these capacitors typically come out in microfarads here. And let me first show you that if you try to implement this amplifier on an IC, the capacitors will become, capacitors are difficult to make on an IC here. There are several ways of making a capacitor on a piece of silicon. One of the ways of doing it is using SiO2, silicon dioxide, as an insulator, depositing metal on top, and using the silicon here itself as the other plate of the capacitor here. And we all know then the capacitance is epsilon by T oxide, which is the thickness of the oxide here multiplied by the area. And oxide permittivity is 3.9. You can use different kinds of thicknesses of SiO2. I've taken a typical value, let's say 20 nanometer, 200 angstrom. And based on that, what we find is that for a 10 microfarad capacitor, the area turns out to be 57 centimeters square. All right, which tells us that large values of capacitors are impractical. A typical size of a IC may be a few millimeters by a few millimeters. An IC containing hundreds of thousands of transistors would be a few millimeter by few millimeter, and therefore this kind of a capacitor is something that you can't really build here. Okay, and the capacitors that you can build then are of the order of a few picofarads only. Realistic capacitors which occupy reasonable area would be a few picofarads, and few picofarads would then imply, all of you know, cutoff frequencies is inversely proportional to capacitance, and few picofarads would imply cutoff frequencies, lower cutoff frequencies, which are very, very high, and it just makes the whole amplifier impractical here. All right. So then the problem is we have to make these amplifiers. If you want to make it on an IC, you have to make the amplifiers without these coupling capacitors. You can't use these capacitors because you cannot implement these large values here. All right, so we have to look for a solution then where we bias this particular transistor in forward active mode. We apply the signal as well. We couple it to the load as well without using any of the capacitors. So in that direction, note that I cannot simply remove CB and CC and CE here. As an example, if you remove the base coupling capacitor here, then you know that when you do DC analysis here, this point gets connected to ground, and therefore your transistor is actually biased in cutoff mode here. So obviously the solution is not trivial where you simply remove the capacitors here. All right, one of the ways of doing it is as follows, partially at least. Note that here what we were doing was biasing it R1 and R2. So biasing requires that the base voltage be of certain value here. All right. And we were using R1 and R2 as a voltage divider to make the base voltage a certain value. And this base voltage minus the VBE drop makes emitter voltage a certain value, and that divided by RE gives us the biasing current here. So one of the ways of avoiding the base coupling capacitor is not to bias it from this side, but use a negative supply here. Use a negative supply and use an RE here. And you can use now, you can easily calculate that under DC analysis, this point is ground, or under a bias point analysis, this point is ground. So I have minus 0.7 volt drop here. And depending on the VEE and RE, I can have any value of current that is flowing, right? So I can bias it at any current that I want. And this current then would obviously be equal to collector current as well. So we can avoid the base coupling capacitor by simply using the negative power supply here and with an RE to bias the transistor here. So that, and the input signal then is directly coupled. So that problem is easily resolved. I'm not talking about the output coupling capacitor. All that we need to do is we have to make sure that the next stage, we can directly connect the first stage to the next stage. And all we have to do is make sure that the biasing of the next stage, whatever is the base voltage or whatever, is compatible with the collector voltage here. So we'll have to design each one of these stages so that the biasing, whatever value you get here, is compatible with the value that is required at the next stage. All right, so we'll simply remove the collector coupling capacitor here and design it in such a way that things work out. The remaining problem is the emitter bypass capacitor. And note that I can't simply remove RE. If I remove RE here, then the voltage itself becomes minus VE, obviously, which is not correct here. All right, and okay, so this is what we are saying, that we can design this particular circuit. Now, if I remove CE here, all right, so let's look at it. What happens if I don't put CE here? So I need RE for biasing. Let me remove CE. If I do that, the gain one can show approximately is equal to minus RC by RE. All of you know that the gain is actually equal to GM times RC divided by 1 plus GMRE. And if GMRE is large, then you can neglect 1 and you end up getting gain which is minus RC by RE, approximately equal to. All right, so let's look at how large a gain can we get if I remove the bypass capacitor. So RC, if you note now, I'm going to calculate RC by RE. So if I look at ICQ, the bias point, one of the ways of calculating ICQ is nothing but this is 0. So this is minus 0.7. So minus 0.7 minus VE divided by RE gives us ICQ. That's one expression here. The other expression for ICQ is VCC here minus whatever is the collector voltage divided by RC. So that's another expression for ICQ. Obviously, the condition which really determines is this one. In fact, so you determine ICQ from this condition, you plug it here, and that decides the value of ICQ. Anyway, we have two expressions. We can equate them together. And once we equate them together, what we get is, after equating, RC by RE. So you get RC by RE by equating these two expressions. And this is what I have put it in this expression here. And so we get the magnitude of gain as VCC minus VCQ minus 0.7 minus VE. And looking at this expression, obviously the gain will be less than VCC divided by minus 0.7 minus VE. And most of the time, we use symmetrical power supplies here. If we use plus 5, we use minus 5, plus 12, minus 12 here. So suppose this is plus 12 here. And so we put here 12. And this is minus 12 here. So we put minus 12 here. We get 11.3. And therefore, it shows you that the gain of this amplifier is practically will always be close to 1 or less than 1. All right. So if you if you remove bypass capacitor, you will not be able to build up gain. Gain will be, you can see here, gain will always be less than this value. So what we have to do is, we can't remove the bypass capacitor. All right. If we can't remove the bypass capacitor, we have to keep RE, because for biasing we need RE here. So now we are caught in a situation where RE is needed for biasing, and we need a bypass capacitor to develop enough gain, and bypass capacitor is something that we cannot implement on an IC. All right, so now the issue then becomes, how do I get rid of CE? I can't implement CE, right? But I can't implement CE. So, the issue then is I want to remove CE here from this place, and instead of that, put something else. Instead of CE, put something else here. Something that I can implement on a piece of silicon, and something which will do the role of CE. Something which will perform the role of CE, but can be easily implemented on a piece of silicon, on an IC. So that's what we are looking for. So we would like to bias it using this negative supply in RE, and we would like to bypass it also, but not through a capacitor. Okay, so that's the problem. We would like to bypass this particular node here, but not via capacitor. So now think about what is the role that capacitor is playing. Do you really need a element which which is a capacitor, something which offers a 90-degree phase shift between current and voltage? Is that what you're looking for at this node? What is it that you're really looking here? We've used a capacitor, but what you're looking for is something which offers a very low impedance path under small signal condition. That's all. And under DC condition, what are you looking for under DC condition? High impedance, or is something which will not disturb the current here. Biasing, which will not disturb your biasing, right? That's what you're looking for. So you're looking for an element which is small signal, under small signal conditions, it's a very low impedance, and it does not absorb the DC part here. All right, so let's replace it by an element X here. We don't know what it is. Take the capacitor out, put an element X here. Under small signal condition, what will X act like? Any two-terminal element X acts like what? Acts like a resistor. Right? So under small signal condition, what will happen is this will be Rx. And what are you looking for? Rx, which is much smaller than Re. Rx, which is much smaller than Re. So this node becomes like a practical small signal ground. That's what you're looking for. So a two-terminal element X, which under small signal condition gives you a very small resistance here. Do we know something like that? Something which can be easily implemented on a IC. So the answer is I can use a transistor itself. A transistor, if you look at it, if I look at it from the emitter side, the transistor gives you a very low impedance here, 1 by GM. Transistor looks like 1 by GM, and note that if I bias it at 1 milliampere current or 2.6 milliampere current, GM is 1 by GM will be 10 ohms or so. Okay, and so this is a very small impedance. So why not take this element X here out and use the transistor itself? Okay, and let's do that. So we are going to take this particular node and connect it to the emitter, and base we will ground, and collector we have to bias it in forward active mode. So collector we can connect it back to VCC. So let's do that. Okay, so we've connected it here, Q2, and transistor is a three terminal device here, so we connect it to VCC here. So if we look at this particular circuit here, all right, and signal of course is being applied here. We'll come to DC bias in a moment, biasing part in a moment here. Let's calculate the gain. So when I calculate the gain here, note Q2 will appear as 1 by GM. So this is my small signal circuit, and my gain then becomes RE typically will be much larger than 1 by GM. So RE can be neglected here. We put 1 over GM2 here. And this circuit we can easily analyze. The current gain will be GM1 times RC divided by 1 plus GM1 by GM2. Okay, GM1 times this resistor here. So that will be the gain. And if both the transistors Q1, let's say you have some biasing current here, and note that if you have a biasing current here, then under DC or biasing condition, this point is ground and this point is ground. And if the transistors are identical, this current will divide equally between Q1 and Q2. So therefore, under biasing condition Q1 and Q2, bias currents will be the same, and therefore the GM of the two transistors will also be same. So GM1 by GM2 is basically equal to 1, and therefore gain that you get is 0.5 GMRs. So, so what we have seen is that we can take the capacitor out and replace it by a transistor. It doesn't act as well as a capacitor here, but we are able to develop reasonable amounts of gain. There's a loss of factor of half. The gain that we develop is half here. We'll see that we can get rid of this half also. As we further develop this particular amplifier, we can get rid of this half also and get a gain which is simply equal to GMRs. And therefore, we are able to build an amplifier which you can see here, which will not use any capacitors anywhere in the circuit. And we'll be able to get large values of gain. So this is then our solution that we use Q2 to bypass RE here. And as I just said, that if you have a current IE here, then note that current IE bias point, so this is ground here, the current that flows in the this emitter, this resistance here will be equal to, this voltage will be minus 0.7 minus VE by RE here. And so that's the current here. And this current, as I said, if Q1 and Q2 are identical, the current will divide equally between these two, and therefore the currents are ICQ1 equal to ICQ2 equal to 0.5 I. Yeah. So you've biased it also. You've biased the transistor Q1 in active region at whatever value of current you want, whatever value of ICQ1 you want. You can adjust it by adjusting the value of RE, and therefore the biasing is also done. And we just saw that you are able to develop a gain at this particular node, which is equal to 0.5 GMRs. All right. So there's a loss of factor of half, but the gain you can you can easily build gain of 50 or 100 or whatever, any amounts of gain using this particular stage. Note also that we could replace RC by an active load here, and therefore build very large amounts of gain. Okay, so this is just a simulation result which shows you that the circuit works fine here. You can simulate this circuit in a microcap and verify that the current is dividing equally between the two halves here. Okay, so here we have used 11.3K and minus 12 here, and note what happens is the current here is 1 milliampere in this, and the current almost divides equally amongst the two here. 485 here and 512. There's slight differences here between the two currents, and the reason being is note that we have directly connected this particular node to VCC here, while this node is connected to VCC through 12K here. So the collector voltage of this transistor is different from collector voltage of this transistor, and we know that current depends on collector voltage also due to the early effect. Okay, and the small differences that you see here, this is 485 and this is 512, that is coming about because of the early effect here. And in fact, what I can do now, the other thing is, note there are no capacitors in the circuit, so I can even amplify a DC voltage. If I have a very small DC voltage coming from, let's say, temperature sensor or pressure sensor or whatever it is, a DC voltage here, you can apply a DC voltage also and amplify it. So it can amplify a DC, AC or whatever it is, and therefore the frequency response, if you see here, there's no lower cutoff frequency at all because we don't have any coupling capacitors. So it amplifies right from DC onwards to some higher frequency determined by internal transistor capacitors. Okay. All right. Now, see, so this is the solution that we arrived at. We saw that there's a little bit of difference between the currents of Q1 and Q2 because of RC. What we can do is, we can make the circuit symmetrical also. If we can take RC that you see here, we can add an RC here as well. We can add an RC here as well. And then what happens is, the two circuit will become perfectly symmetrical. The current that you have here will divide equally between these two halves. Okay, so we can do that. Not only that, one could think now that I can put an RC here, and this node is also available to me. Maybe I can apply a second voltage here as well, as a general case. If you don't want the second voltage, you can always put it to ground, and then this is a amplifier with single input here. But it opens up a possibility that you could apply a second input here as well. An input from this side and an input from this side. So you can have an amplifier with two inputs going into it. And it also opens a possibility that I can take an output here at this node and I can take an output here as well. So I have two outputs, I have two inputs. Not only that, I can define an output which is not between this node and ground or between this node and ground. I can define an output which is between this node and this node. I can define output as between these two nodes here, between this node and this particular node. All right. So it is opening up lots of interesting possibilities that I can apply input from this side. I can take output here, I can take output here, and I can take outputs between the two nodes and stuff. Okay, so now we are moving towards, so recall that our goal was to build a common emitter amplifier without using any coupling capacitors so that we can implement in an IC. We arrived at this particular solution and we can see that we can generalize it to this particular amplifier. And we have arrived at a configuration which is called a differential amplifier. Differential amplifier which has two inputs here. Two inputs, VIN1 and VIN2. And if you are interested, you can take, as I said, you can take a single-ended output here, or in between you can take a output here. Now, differential amplifiers, as the name goes, is an amplifier which we will just see is sensitive to the difference of the two voltages. Whatever is the difference between the two will get amplified, and whatever is common between the two voltages here will get rejected. So, what I mean by that is, if I look at the output voltage here, the output voltage here will be sensitive to, we'll just show you difference between these two. Right? It will be sensitive to the difference between these two, but the output voltage here will not be sensitive at all to what is common between them. So, for example, if I apply 0.5 volt here and a 0.5 volt here, you'll find V0 is something. If I change it to 1 volt here and 1 volt here, you'll find V0 is not changing. It's not responding. On the other hand, a small difference between, if you apply 0.5 here and 0.49 here, you'll find V0 changes a lot. So it's sensitive to the difference between the two signals here and insensitive to what is common here. So there are a couple of definitions here. So we are talking about an amplifier now of two kinds. Both are differential amplifiers. In this case, the input is differential in nature. We have two inputs, VI1 and VI2. Output is a single-ended. In this case, we have two inputs here, and the outputs are also two here, V01 and V02, and we take actually the output as the difference between the two. The actual output voltage is V01 minus V02. Okay? And so a couple of definitions. We'll focus primarily on this kind of an amplifier here. So in a differential amplifier, people talk about two things here. As you can see here, there are two inputs, VIN1 and VIN2. I can take these two inputs and define two new quantities here. One is called differential input voltage, which is the difference of the two voltage here. And the other one is common mode input voltage, which is average of the two. The average of the two basically tells us what is common between them, between the two voltages here. All right. So I have two, given VI1 and VI2, I can define a differential input voltage and I can define a common mode input voltage. Note that the output voltage then, output voltage obviously will depend on VI1 and VI2. But instead of talking about VI1 and VI2, note that you can also talk about VID and VIC. Given VID and VIC, you can find out what is VIN1 and VIN2. So either you can talk in terms of the two input voltages, or it's equivalent to talk in terms of differential input voltage and a common mode input voltage. All right. So V0 we can write as it depends on VID, differential input voltage, and it depends on common mode input voltage here. And because both are voltages here, the two are related together through the gain expression here. So this is what we call as differential mode gain, and this is what we call as common mode gain. So it tells us that the output voltage depends on differential input voltage through this parameter called differential gain, and it also depends on common mode input voltage through the parameter called common mode gain. And so differential mode gain and common mode gain. And in a differential amplifier, is one of the chief characteristics is that AD, differential mode gain, is much, much larger than common mode gain. So the output voltage is sensitive to VID and is not sensitive to VIC. Okay, so that's the property of a differential amplifier. And the ratio of the two is what we call as common mode rejection ratio. AD by ACM it tells us how large is the common differential gain relative to the common mode gain. And the name of this particular ratio is appropriate. It tells us common mode rejection ratio. So it's telling us how efficiently does your amplifier reject the common mode signal. You know, if ACM is very, very small, then it's very efficient in rejecting common mode signal here and amplifying the differential mode signal here. So the ratio characterizes the property of differential amplifier, the chief property of differential amplifier, which is high differential gain, low common mode gain. Okay. So these are some basic definitions here. As an example, an amplifier like this is fairly easy to build. A differential amplifier with a differential gain equal to 100 and a common mode gain, let's say 0.01. We'll see later on that this is something which we can easily build, an amplifier like this. So just so that you become comfortable with the definitions here, we have a very simple example. Input voltage, let's say, is 1 volt plus 5 millivolts sin omega t, VI1. VI2 is 1 volt minus 5 millivolts sin omega t. So we have two voltages here. And if you want to use the differential pair, what you do is you first calculate what is the differential input voltage here. So VID is V in 1 minus V in 2, which is 10 millivolts sin omega t. Common mode input voltage, which is the average of the two. So you add the two together divided by 2. So that's 1 volt here. So note that in your amplifier, two signals are going in. One is a common mode signal, which is 1 volt, and the other one is a differential mode signal, which is 10 millivolt. Now, although I took a DC here, I could have written here 1 volt sine omega 2, some other sinusoidal frequency. It doesn't change anything. It could be a 1 volt, let's say a triangular wave. It could be any signal here. Just for convenience, simplicity, I've taken it as a DC. So it could be anything here. So a sinusoid, DC, any value here. All right. So this is the common mode value. This is the differential mode value here. We are given these values here, AD and ACM. So our output is going to be AD times VID plus ACM times VIC here. AD is 100. So 100 multiplied by 10 millivolts. So it gives us 1 volt sin omega t. And ACM times VIC. ACM is 0.01 common mode gain. And that multiplied by 1 volt gives us 10 millivolt. All right. So now what you see your differential amplifier has done. The input had a large common mode value, 1 volt and 1 volt here. And that has gotten totally rejected. It comes out as 10 millivolt. And the differential input was 5 millivolt minus 5 millivolt, 10 millivolt sin omega t. The differential input has become amplified and appeared over here, 1 volt sin omega t. So common mode signals are getting rejected. And what is the difference between the two is getting amplified and appearing over here. Okay. So this is the property that you have to remember. Whatever is common is rejected. Whatever is different is amplified. All right. Is this amplifier useful? Can we think of applications for such an amplifier? All right. So there are many, many applications. One is, of course, note that this differential amplifier that we are building in the manner that I've indicated it solves a biasing problem. That we don't require any coupling capacitors and we can bias the amplifier and apply the signal also. All right. Okay, so this is our differential amplifier. Simple differential amplifier. So this is with a resistive load here. The two inputs are over here, and V01 and V02 are the two outputs. We'll take, as I said, output can be taken at any place here. Okay. So whether you focus on V01, we'll show you. V01 you will find is sensitive to the difference of the two, V in 1 and V in 2. Or if you want to use V02, that is also sensitive to the difference between V in and V in 2. And we will show you later on that magnitude of V01 is same as magnitude of V02. The only thing is V02 is 180 degree out of phase with V01. That's the only difference between the two output voltages here. 180 degree phase shift between these two here. All right, let me show you one advantage of differential pair which you can use, which is for rejecting unwanted signals here. See, this is, if you look at this particular figure here, we have basically a common emitter amplifier. If you look, a common emitter amplifier with a bypass transistor here, bypass capacitor here, and forget this for a moment here. And we have a normal voltage, input voltage, which is being fed into your common emitter amplifier, right? A common emitter amplifier, the input is being fed, and the output, of course, is from here. So it's a normal common emitter amplifier. What I've done is, suppose a noise voltage gets coupled into your amplifier. Somehow, let's not worry about how it gets in. There is a, somewhere you have another amplifier or something else, and this is getting coupled into your amplifier here, capacitively coupled into your amplifier here. Now, obviously, if it gets, this is the noise voltage, it gets coupled into your amplifier, which means that the input will get corrupted, right? Input will get corrupted here by the noise here. And if the input gets corrupted here, the output will also get corrupted here. So let me show you. This is my noise signal here. So this is my input. Normal input was supposed to be a sinusoid here. Normal should have been a clean sinusoid, and now I have put in some value here, and so you can see it's a noisy input here. All right, noisy input. Inputs are small in magnitude because, all right, the output is noisy also. That's the output here. The output, because the noise just, my amplifier cannot distinguish between the input and the noise, so it just goes in. Okay, and the output is also noisy here. But now let's see how we can use the differential amplifier. So this is the differential amplifier. The input I apply from one side. I don't apply any input from the other side. Okay. Now noise which is coming in into my noise, we are assuming gets coupled into both sides here. But whatever is the external source of noise, it gets coupled to this input also and this input also. I don't apply any input on this side though. Okay, but noise is getting coupled on both sides. So now what will happen? If I look at, this is a differential amplifier. This input is noisy. This input is also noisy here. But the noise input is what? Is common mode. The noise input is coming from both sides here. Is common mode. And the signal is actually differential. Signal is only being applied from here. Signal is not being applied from here. The signal becomes differential in nature. The noise becomes common mode in nature. And therefore, note that what will happen is the same. Inputs are noisy as usual. Output is totally noise free. You can go ahead and do this here and check V0 here. There's no noise in the output at all. Just got completely rejected here. So there are many situations here where, you have a wire coming into your system and noise is getting coupled into it. Okay, one signal that is coming in, let's say coming from some place and noise is getting added to it. What you can do is you can run another parallel input along with your real input. So noise will get coupled into that as well. But then you apply it to one side here and you apply it to the other side here, and the two just cancel each other. Okay. But note, what we are assuming here is that the noise is deterministic in nature. Noise is deterministic in nature here. Okay. Or there's an assumption, not really. The assumption is that the noise that is coupled here is exactly the same as the noise that is coupled. That you have to arrange in your system, that whatever is the source of noise, you have to build the system in such a way that whatever is the source of noise that is getting coupled here also affects this input also. You have to design it, or you have to implement it in such a way that the noise gets coupled into both sides. Okay. So if the noise is identical on both sides, then the two will cancel each other. So that's one very, very important property of differential amplifiers here, that you can reject unwanted noise. The other one, let me show you another place where differential amplifiers are commonly used. Yes. Huh? Phase of? No, the noise is the same. Same noise is getting coupled here. The output is, this is the output voltage here. So output voltage, as I said, if you look, output voltage is 180 degree out of phase with the input. Okay, so input is this thing, output is 180 degree out of phase. So which is fine. Phase doesn't matter here. Okay, phase change or between the input and the output. What we are saying is the noise is the same and you don't see any noise at the output. Okay, you're recovering only the signal. Okay, let's look at this particular example here. We have a situation where you want to amplify a small signal which is immersed in a large unwanted signal. Okay, let me show you an example here. Suppose this is a pressure sensor. Okay, this is a pressure sensor, and so what happens is, as you apply pressure onto this particular sensor, its resistance changes. Okay, its resistance changes, and the change in the resistance is very small. Okay, and you want to detect small changes in pressure, and therefore the changes in the resistances are also very small here. So now, how do I detect the small changes in resistance and translate it into a voltage? So one way of doing it is, I build a voltage divider here, and note that when I build a voltage divider, as my resistance changes, the value of this particular voltage will change. Okay. Now, for convenience, what I do is I make the value of, I choose this value such that when no pressure is being applied, R0 is equal to R. Okay, so the nominal value of Vx is what? 0.5. 0.5 VCC here. That's the nominal value. Now, when the pressure comes in, this resistance changes and the value of this particular voltage will increase or decrease or whatever happens above 0.5 here. So what happens is, the value of this particular voltage can be expressed as follows here, approximately. That nominal value of Vx is 0.5 VCC. When you apply a pressure, there is a small change in delta R, and the small change translates into an extra voltage here, which is 0.5 VCC delta R by R. Okay, very easily you can add a R plus delta R, simplify it, and show it that this is equal to that. Okay, so note that the voltage that you are getting has a unwanted component here, and has a signal component which you are interested in. This is the one which is proportional to delta R, and this is what carries information about the pressure applied here. So you are interested in the signal, but the signal that comes in along with a unwanted signal, and this is something which is very small, let's say 1 millivolt or 2 millivolts, and you would like to amplify it, but then it comes in along with this. So the issue is, that's what I'm trying to tell you, is that you have a small signal which you are interested in, but it comes immersed in a larger signal which you are not interested in. Now, obviously, I cannot simply take this particular as an example. All right, so VCC is, let's say, 5 volt, delta R by R naught is 1%, Vx turns out to be 2.5 plus 25 millivolt. So you're talking about 25 millivolt signal here, immersed in 2.5 volt. Note that both the signals are DC. This is also a DC here. When you apply a steady pressure, the resistance changes by a certain amount, and this is also a DC. So it's not that one signal is an AC, the other one is a DC, you use a capacitor to filter out. Both of them are DC here. So filtering is not an option that is there for you. Okay. All right, so how do we detect and amplify this particular signal here? Obviously, this solution will not work. That I simply take my signal, put it into an amplifier. What will happen is, it will amplify 2.5 volt multiplied by 100, and this will go to, it will simply saturate it. It will simply saturate it to power supply voltage here. A simple amplifier will not work. This signal itself will saturate it, and you will not be able to detect this. So a solution to this is the following. Is a differential amplifier. This is my sensor part here, R0 and R here. And this is where I get the voltage, which is the voltage that I want to detect and amplify. What I do is, on the other side also, I build a parallel system here, which is R0, and I don't put a sensor here, I put an R0 here as well. So what I get here is 2.5 volt plus 25 millivolt, the actual signal here, and here is all that I get is 2.5 volt here. So this, I put it into my differential amplifier. So whatever is common, 2.5 volt is common, will get rejected, and the output will be sensitive to only the signal here. All right, so only the signal will appear at the output, and the common mode input will get rejected here. So routinely, what you find is differential amplifiers are used with sensors to detect the small changes in voltage here. Okay. All right, so this is showing you the same thing. On one side, I put only 2.5 into my differential amplifier. On the other side, I put 2.5 plus whatever is the signal here. And in this case, signal I applied as a sinusoid, but it need not be a sinusoid. And so the signal only appears over here. Okay, signal only appears over here. at this point, and 2.5 volt here, 2.5 volt here do not do much to the circuit here. It doesn't have much influence over the circuit. Okay, I'll skip some of these things here. All right, so we've seen that differential amplifier then is a natural solution to building an amplifier on an IC. Here is an amplifier which I'm able to bias through this negative supply voltage in RE without, and I'm able to apply my input also without requiring any coupling capacitors. No coupling capacitors anywhere in the circuit, no external capacitors anywhere in the circuit, and therefore this circuit, differential amplifier, can be easily built on a piece of silicon, efficiently built on a piece of silicon here. The other one is it has very important properties that it amplifies differential mode signal and rejects the common mode signal. The next thing that we have to do is do a more detailed analysis of this particular amplifier. All right. So as usual, you can either build using NPN or you could build using PNP. It's the same circuit, except that note that it gets reversed here. Emitter is at the top, gets connected to this end here, and exactly the same. You can, now that we are familiar with MOS, you can build it with a MOS also. Take a NMOS here and an NMOS here, add a resistor here. These are the two resistors in the drain end, and this amplifier also works in the same manner. Okay, so you have a MOS differential pair. Of course, I can replace it by a PMOS also. So you get a PMOS differential pair also. And I'm sure what you can imagine now, I can do with this particular amplifier further. If you note that this amplifier, it actually evolved, the way we did it, evolved out of a common source amplifier. Common source amplifier, and it evolved out of a common source amplifier with what? With a resistive load. Now, if you want to build a large gain, what can you replace RC by? You can replace it by a transistor. So I can easily replace it by a transistor here, right? Not only that, I can replace this by sort of a cascode pair here. Not only that, I can replace this by a cascode load also. So we are starting off with a very simple differential pair with a resistive load that you see here. But with the things that we have already learned, we can very easily now, without requiring, we've already covered the reasons for that. We can replace it by a transistor. We can replace it by two transistors here. We can replace this by a cascode. And you can also see the following. What is the purpose of this REE here? To supply a bias current, right? The REE is there to nothing but to supply a bias current. And remember, when you're building things on an IC, you don't want to use resistors. You want to minimize resistors because they occupy a large area. So as much as possible, take a resistor out and replace it by a transistor. So if this one is there just for biasing, I can take this resistor out and replace it by a transistor also. All that you require is that I should have a current source here. And this current source will supply current to here and here. So I can take this out and replace it by a transistor and bias it in saturation, in active region. So we can imagine now how our differential pair is going to evolve. I'll replace it by a transistor here. I can replace it by a transistor here, replace a transistor here. I can replace it by two transistors here, a cascode connection here, and that's how differential pairs will change. Okay. All right, but before that, yes. Can we replace what? Resistors by transistors. This, of course, we can replace, and this one also. Huh? No, you cannot make a general statement that everywhere where I have a resistor, I can make. All general statements, all absolute statements are wrong. Okay, in general, I would say all absolute statements are wrong. Okay, so you have to go situation by situation. We see here that as a load, we can use RD. As a load, we can replace RD by a transistor. And this is nothing but a biasing. And we have seen at several places current source biasing. So we know here directly that this can be replaced by a transistor here, this replaced by a transistor. So in the context of amplifiers, in the context of biasing, yes, I can do it. But I don't want to make any absolute statement. There are places where you can't do it. Okay. Alright, so what we have to do then is a bias point analysis, a small signal analysis of this amplifier here. Now, there is one important point that you have to remember in these amplifiers. And that is that this is an amplifier which can amplify DC, AC, or whatever it is. Alright, so deliberately we will not call now a DC analysis. DC analysis can be highly misleading because my input signal can also be DC. Alright, so DC can be highly misleading. What we will call now as a bias point analysis. What do I mean by bias point? When I don't apply any signal here. So when I put it to ground and I put it to ground, I have no signal in my circuit here and I do a bias point analysis, which means whatever are the voltages, normally whatever are the voltages at these nodes here. That's a bias point. In this case, the bias point happens to be a DC, which is fine. Okay, so we are doing a DC analysis. But note, when we do small signal analysis, obviously this point will become ground, this point will become ground, all that will happen, and we'll only apply the small signal voltage. Now, the small signal voltage that you apply can also be DC. Note, small signal voltage need not be an AC. Please get this out of your mind. The small signal voltages always have to be DC. All that we are saying is that there is a signal here and its magnitude is small. How small? Well, small enough to treat these transistors and this amplifier in a linear manner. That's all. Alright, so there will be situations where we'll put a signal here which is a DC and we'll be doing a small signal analysis. And you can say, well, are you doing a DC analysis? Yes, in a way I'm doing DC analysis also because the signals are DC. But I'm treating those small DC signals as small signal and I'm treating them through a small signal route. Okay, so separate the analysis into two parts. One is bias point or quiescent point analysis and the other one is small signal. We will not use the term DC to avoid the confusion here. And in all of these, with the amplifiers that we have studied, the analysis is pretty straightforward. So you remove the sources here, remove the source here, and what you do is you calculate the current here. So we know that this is 0 here, this is 0 here. You calculate this current here. So this is minus 0.7. If this is minus 0.7, this voltage is known. So you can easily calculate what is IE, this emitter, this current here flowing in the emitter resistance here. That's easily calculated. And throughout our analysis or discussion, we'll assume Q1 and Q2 are identical. They are matched. Okay. And therefore, this current and the circuit is totally symmetrical. So this current is going to divide equally between these two. So my bias current or quiescent current here and here is nothing but 0.5 IE. So bias point analysis is straightforward. All that you have to do is calculate this current and just divide it into half and you get the two currents here. This voltage you can easily calculate now will be VCC minus the drop here, and this also is the same VCC minus drop. All right. So the bias point analysis is straightforward. Now in fact, there are three kinds of analysis that people do. One is a bias point analysis that I just showed you. Another analysis is where the inputs are applied and the inputs are small in magnitude. Okay, which is a normal small signal analysis here. There's another possibility where I'm applying an input and the input is no longer small. It's no longer small to be considered as small signal. Right? So what do we call it? We call it large signal analysis. I'm doing a signal analysis for a signal input, but I'm doing it for a large signal. So that's another possibility that is there here. All right. Okay, so let's stop here and we'll continue then.